Welcome to question 7 of our problem solving series wave 1. In this question, we are going to see how all the rules of studied so far, quotient rule, product rule, chain rule, trigonometric, exponential, and logarithmic differentiations can be combined into one tough looking expression. Let's dive right in. First of all, what does this question ask us to do? It tells us to differentiate the function y equal to tan x times e to the power ln of x squared plus 1 all divided by x. At first glance, this looks terrifying, but step by step we'll break it down. So what's the first thing we have to do? Notice that the numerator has the tan function and an exponential function with a log inside. Then the whole thing is divided by x. So firstly, we're going to simplify this equation. Let's not say simplify, but partition this equation. Let's start with our numerator. Our numerator, first of all, we notice that this function can be expressed as a numerator divided by denominator, which tells us that it can be expressed as a rational function. Hence, we will have to use the quotient rule. So in the quotient rule, what's our first step? We identify our numerator followed by our denominator. So let's start with our numerator. We will say let f of x equal to our numerator tan x e to the ln of x squared plus 1, and g of x, our denominator, be equal to x. So what does the quotient do? Let's recall. It states that the derivative with respect to x of any rational function of the form f of x on g of x is equal to bottom d top minus top d bottom all over bottom squared. We'll call this our equation 1. Yes, I decided let's start labeling our equations to facilitate the solving of the equations and to ensure cohesion between the solutions, throughout the solutions. Sorry. So that's our first equation. In this equation, we notice that we're having several terms. We have f prime of x, g prime of x, and g of x all that square, which we don't yet have. So let's start with the first term, f. Let's start with g prime of x. Why g prime of x? Because g of x is simpler. Yes, so let's just start with it, since f of x is going to take us a lot of time to differentiate due to its complexity. So g prime of x, which is equal to the derivative with respect to x of g of x, which is the derivative with respect to x of x, is the function 1x to the power 1 minus 1, which gives us 1. We call this 2. Let's move on to, yes, so we're going to move on to our next function, g of x squared. So g of x all that squared is equal to, what is g of x? X all that squared, which gives us x squared. Equation 3. Now let's calculate this term. Since we have g prime of x and we have f of x, let's calculate this term. F of x times g prime of x is equal to, what is f of x? Tan of x e to the ln of x squared plus 1 times g prime of x, 1, which gives us tan of x e to the ln of x squared plus 1, the same function. We'll call this equation 4. So if you notice, we have already calculated our first term and our second term. All it's remaining us is this term. But in order to calculate this term, we first need to calculate f prime of x. So let's work it out. Let's calculate f prime of x. So first of all, let's recall what f of x is. F of x is the function tan x e to the ln of x squared plus 1. So what's the first thing we can notice here? F of x is the product of two functions. One function, which is trigonometric function tan x, and our second function, which is an exponential function with a logarithmic function integrated in it, e to the power ln of x squared plus 1. So first of all, we notice that f of x is the product of two functions. And when we notice that a function can be expressed as the product of two functions, the first formula or the first law or the first rule that comes to our mind is the product rule of differentiation. So first of all, let's recall this product rule. What does this product rule state? The product rule states that the derivative with respect to x of two functions u and v is equal to u dv plus v du. So first thing, what is our u and what is our v? So we will let u be equal to the function tan x and v be equal to the function e of ln of x squared plus 1. Now let's start with our derivative of u. Du on dx, which is equal to u prime, is equal to d on dx of tan x. And recalling from our derivative of trigonometric functions where we worked out, we proved the derivative of tan x with respect to x. If we can recall well, we notice that this gave us the trigonometric function sec squared x. So I've calculated u prime. Let's go to v prime. So first of all, what is v? V is the function e to the power ln of x squared plus 1. Let's recall when we're still working on the derivative of exponential functions, it was well stated. It was well stated that the derivative with respect to x of any function of the form e to the power g of x is equal to g prime of x e to the g of x. So what is our g of x in this case? This box was too big. I just want to reduce the size of the box. So what is our g of x in this case? Our g of x is this function. So let's not call it g of x, since we already have g of x here. Let's use h of x in this case. Let's just wipe it out and write it down fast. H of x is equal to h prime of x e to the h of x. Yes, we changed it to h of x to ensure coherence. We cannot use g of x on top here and then we use again g of x. People might not understand, or it might make the solution a bit blurry. That is less comprehensive. So let's use h of x. So first of all, what is our h of x? Let h of x be equal to ln of x squared plus 1. Now, we still recall very well when working with the derivative of logarithmic functions. It was well stated that the derivative with respect to x of a function ln of, what should we use this time? Let's use n of x is equal to n prime of x on n of x. Sorry if there are many recalls. Yes, it's just that the function is a little bit complex, but I'm sure it's at least coherent enough and well enlisted for easy comprehension. So let's work with this. What is our n of x? We all know. Let n of x be the function x squared plus 1. This implies that n prime of x, which is the derivative with respect to x of the function x squared plus 1, is equal to the derivative with respect to x of the function x squared plus the derivative with respect to x of the function 1, which gives us 2x plus 0, recalling power rule and the constant rule. Power rule, which is the derivative of x to the power 2, is 2x to the power 2 minus 1. Constant rule, which states that the derivative of any constant gives us 0. So this then implies that the derivative with respect to x of h of x, which is h prime of x, is equal to derivative n prime of x on n of x, right? What is n prime of x? 2x on n of x, x squared plus 1. Perfect. But if you can still recall, we calculated h prime of x in order to calculate v prime. Why? Right? We notice that v was equal to e to the power h of x. Implies that v prime is equal to h prime of x e to the h of x. This implies that v prime is equal to, what is our h prime? 2x on x squared plus 1 times e to the ln of x squared plus 1. So I've calculated v prime, we've calculated u prime. We know u, we know v, we can then find f prime of x. Hope is comprehensive enough. Sorry. So let's calculate then. f of x was a function u times v. So f prime of x was a function u dv plus v du. So f prime of x is the function u dv plus v du, which give us, let's start with u. What is our u? Our u is the function tan x. What is our v prime? V prime is the function 2x on x squared plus 1 e to the ln of x squared plus 1 plus, what is our v then? Our v is the function e to the ln of x squared plus 1, e to the ln of x squared plus 1. And what is our u prime? Our u prime is the function sec squared x. So let's simplify this. We have our expression, but we need to simplify it. It looks a bit complicated, a bit complex. So we're having two terms in this equation. What is common in both terms? The first thing we can identify as common is the expression. E is the term e to the power ln of x squared plus 1. So we can factorize that out. E to the power ln of x squared plus 1 in bracket. What is remaining? We have 2x tan x on x squared plus 1 plus sec squared x. So I found f prime of x. But recall, let's write it down again, much more clear. X e to the power ln of x squared plus 1 in braces 2x tan x divided by x squared plus 1 plus sec squared x. We can call this equation equation 5. So we then move on to previous equations. Why were we looking for f prime of x? We were finding f prime of x in order to calculate the term g of x times f prime of x. So now that we have our f prime of x, let us calculate the term g of x, f prime of x. But first of all, what is g of x? If you can recall, this is it above here. G of x is the term x. So g of x, f prime of x gives us x e to the ln of x squared plus 1 braces 2x tan x on x squared plus 1 plus sec squared x. Equation 6. So if you notice now we have our first term g of x, f prime of x, which is our equation 6. We have our second term f of x, g prime of x, which is our equation 4. We have our third term g of x order squared, which is our equation 3. So in order to calculate the derivative of our function, of our complete function y, which is this first term minus this second term divided by this third term, we just substitute it perfectly. So let's move on. Let's substitute dy on the x is equal to our first term x e to the ln of x squared plus 1 in braces 2x tan x on x squared plus 1 plus sec squared x minus our next term, which was f of x g prime of x. F of x g prime of x was this term tan x e to the ln of x squared plus 1 minus tan x e to the ln of x squared plus 1 all divided by g squared. And what is g squared? G squared is x squared. The next thing we do is simplify, noticing that e to the ln of x squared plus 1 is common on both terms. We can factorize it out. E to the ln of x squared plus 1, right? In braces, this x enters, this x multiplied by both terms. We have 2x squared tan x on x squared plus 1 plus x sec squared x minus tan x all divided by x squared. Now we can then perform our common denominator on all of this, or simplify all of this. This leaves us with e to the ln of x squared plus 1 in braces 2x squared tan x on x squared plus 1 minus x sec. Sorry, this is plus. I'm the one that made a mistake. This was supposed to be an underline or something. I went and put it and it confused me. Sorry about that. X squared plus 1 divided by x squared plus 1. If you notice, I'm trying to make all of their denominators to be the same. So if I add this denominator in this term, I need to add it again in the numerator in order to avoid a complete change in the expression. Minus tan x squared plus 1 squared plus 1 divided by x. This then simplifies to e ln x squared plus 1 in braces 2x squared tan x plus x squared plus 1 sec squared x minus x squared plus 1 tan x, all divided by x first of all, and x squared plus 1. This x comes from this term here, so that's why it's the way it is. So moving on, let's still simplify. Notice that this can still be simplified. We're still having two terms here which can be simplified. Our first term here is in terms of tan x, and our second term is still in terms of tan x. That means we can factorize tan x out for both terms. This leaves us with e to the ln of x squared plus 1 in bracket tan x was remaining 2x squared minus x squared minus 1 plus, we can send this x, we can send this x here into the bracket, leaving us with x cubed plus x sec squared x divided by x into x squared plus 1. So let's simplify this bracket. This leaves us with e to the ln of x squared plus 1 in bracket tan x, 2x minus x squared as x squared minus 1 plus x cubed plus x sec squared x divided by x squared plus 1. So we can then conclude that therefore the derivative with respect to x of our function was our initial function. The initial function was tan x e to the ln of x squared plus 1 divided by x, which is equal to dy on the x Okay, so now that our differential is done, I'm just going to highlight something we would have done in the beginning of this question, which I never did. Not because I never wanted to do it, but just if we had done it, it would have simplified the question. And yes, it would have simplified the question. I just wanted a much more complex question for us to walk throughout and enable a better comprehension. So if you notice, if you can still recall your logarithmic laws, you know that e, or let's use a general term, a to the log of a, b is equal to b. This tells you that e is the ln of x squared plus 1, which is same thing as e is the log to the base e of x squared plus 1 is equal to x squared plus 1. So imagine we did this simplification in the beginning. What would we have had? We would have had our y being equal to tan x times x squared plus 1. Now the question looks much more simple. It looks a lot more simple. We would have done it simpler and simpler and simpler. But the aim of this exercise is to enable understanding, not simplicity. When you are working, imagine, like, let me, for example, if this was an exam, it would be better for you to apply this simplification from the beginning. But this is not an exam. This is just an example which was made in order to emphasize the understanding of the concepts. Yeah, so the much more complex or the much more concepts that the example entails, the better it is for an example. So that is why I didn't use this substitution in the beginning. I know that there are lots of you guys who are wondering why we didn't simplify it from the beginning. So here's the reason. So let's just apply this simplification to our final answer here. We have dy on the x being equal to x squared plus 1 into x squared minus 1 tan x plus x cubed plus 3 into sec squared x, all divided by x squared plus 1, leaving us with, this cancels this, x squared minus 1 on x tan x plus x into x cubed, x squared, sorry, plus 1 sec squared x on x. X cancels out. We are leaving us with x squared minus 1 on x tan x plus x squared plus 1 sec squared x. So we could still conclude that the derivative with respect to y, with derivative of y with respect to x leaves us with x squared minus 1 on x, all that tan of x plus x squared plus 1 sec squared x. So this is a much more simpler form we would have had, or we have still gotten, using this simplification. Okay, so sorry, there was an error. I was just going through the solutions and I noticed that an x squared here turned to x out of a sudden, all of a sudden. Wow. Well, sorry for that error. Let's just correct it quickly. Yes, squared. We have squared. We have squared. We have, yes, normal there. We have squared. We have squared. We have squared. Squared. We have squared. We have on x still here. Squared on x. And this can be simplified to 1 minus 1 on x squared tan x plus 1 plus 1 on x plus x plus 1 on x sec squared x. Wow, so thanks a lot. I'm sure there aren't any more errors in the question, but thanks a lot, and here is the solution to this question. Okay, so now, just for a test, let's try and simplify the equation from the beginning and then solve it throughout. So given that we simplify the equation from the beginning, what would we have had? We would have had y equal to x squared plus 1 tan x divided by x. So let's solve this question. Let's solve it. So first of all, this can still be seen as a quotient, that is with a numerator and a denominator, and it can still be seen as a product with our first term and our second term. Let f of x be equal to our first term x plus 1 on x, implies that f prime of x, which is bottom the top minus top the bottom on bottom squared. This leaves us with x. What's the differentiation of x squared plus 1? We have 2x plus 0 minus x squared plus 1. Differentiation of x, 1, divided by x squared, leaving us with 2x squared minus x squared minus 1 on x squared, leaving us with x squared minus 1 on x squared, which gives us 1 minus 1 on x squared. So let's then calculate. Let g of x be equal to tan x, implies that g prime of x is equal to sec squared x. This then implies that y prime, which is dy on the x, which is equal to f of x, f times g prime was f squared plus 1 on x times g prime of x plus g times f prime of x. What is our g? Tan x times f prime of x. And this still simplifies to 1 minus x squared tan x plus x squared sec squared x. And this gives us same answer as we have above. So what does it tell us? It tells us that no matter the case, that is whether we simplify or we don't simplify, we come out to the same solution. But without simplification, the work is much more messy, much more complicated, and much more hard to calculate. Whereas with a good and simple simplification, the work or the solution can be summarized to just a couple of lines. So just to advise you guys, when you're having a solution or when you're having a question, the first thing you do is check if that question or that differentiation can be simplified from the beginning. If yes, simplify before differentiating. So in conclusion, in this question, we combine the trigonometric, exponential, logarithmic, product, quotients. We didn't use chain. Yes, we use constant multiplier rules. We use a lot of the differentiation rules in order to solve this question. So in the next problem, we'll go even deeper with the power raised to a power type of function. So thank you. I'm waiting for you guys in the next video. Bye.